You are given two integers m and n representing the number of rows and columns of a grid consisting only the characters dot and hash where free cell and hash represents obstacles in it. Okay. The hash dot represents free cell and hash represents an obstacle cell. A valid path is a sequence of free cells that starts from top left 0, 0 and inside bottom minus n minus 1, n minus 1. Moves only right from I, j to I, j plus 1 or down from I, j to I plus 1 or j. Any grid such that there is exactly one valid path from right path. Okay. I think valid path is 0, 0, 0, 1, 1, 1 and 1, 2. Dot. So we'll take rho equal to n and I'm creating a new integrate. New int of, you just create one row and along with it. What I'm going to do is first I'll fill the row, then later I'll fill the column. So Like any grid such that there is exactly one variable from top to left side. Any grid, like any grid is possible, or only this grid is only required. I have one small doubt. So here I'll be taking and so I think I'll write one more time. It's completed. Yeah, we'll dive into the next question. Lights to illuminate a road. You are given an integer array lights of length n representing positions 0 through n-1 on a road. For each position I, if lights of I equal to v, where v is greater than 0, there is working bulb at position I that eliminates every position from max of 0, I minus v, min of n-1 plus inclusive. Equal to 0, there is no working light at, there is no working bulb at position I. A position is visible if it is illuminated by at least once one working bulb. You may install additional bulbs at any position. Each additional bulb installed at position they illuminate position from to min of n-1 to j+1 inclusive. Return the minimum number of additional bulbs required to make every position on the road visible. So one optimal, first one is 0, 0, 0, 0, and one optimal placement is install an additional bulb at position 1 illuminating the positions 0, 1, 2. Okay, install an additional bulb at position 3 illuminating the positions 2, 3. Therefore the minimum number of additional bulbs required is 2. Oh, question is, if lights of I equal to v, where v is greater than 0, okay, there is a working bulb at position I that illuminates every position from max of 0, I minus v. So for example, we are having a working bulb at position 3, that is 2. Yeah, position 3 that illuminates every position from max of I minus v. So I is 3, 3 minus 2 is 1. So it eliminates till max till 0 to 1. Okay. The position is 1, 2, 3, 4. Oh. Max of I minus v. I is 3 there and v is 2. So 3 minus 2 is 2. To min of I is 3 minus v is 2. So 1 to min of n minus 1. So here n is so 5 minus 1. Okay, 5 minus 1 is 4 and j plus 1 includes, okay, sorry. Minimum of 5 minus 1, 4 to I plus v. So I plus v is 2 plus 1, 3. 3 and 4. So we'll be taking 3 and here max is 1, 1 to 3. Yeah. Since light 3 equal to 2, the working bulb at position 3 illuminates positions 1, 2, 3, 4 because here max is 1 and minimum is n minus 1 which is 4 and I plus v which is 5. 3 plus 2 is 5. So we are taking 4. So it eliminates till 1, 2, 3, 4 positions. So install an additional bulb at 1 illuminates position 0, 1, 2. Yes. If you install here, eliminate all the places, making every position visible. Therefore, the minimum number of additional bulbs is 1. Okay. So here we need to check what is the optimal placement. If you check here, the position is visible if it is illuminated by at least one working bulb. Okay. At least one working bulb. Any position, each additional bulb installed at j illuminate positions from max of j minus 1 to min of n minus 1 and j plus 1 inclusive. Yes. So as there is no bulb here, install an additional bulb at position 1. But here it says the position is visible if it is illuminated at least one working bulb. Okay. So here we have put the bulb. So max of 0 comma j minus 1 which is 0 and min of n minus 1 which is nothing but 4 minus 1 is 3 and j plus 1 is j is 1 here and it makes 2. So minimum will be 2. So 0, 1, 2 eliminating position 0, 1, 2 and the third bulb will be visible to us. Additional bulb at position 3 illuminating the positions 2, 3. Therefore the minimum number of bulb required is 2. Okay. I think for this we can directly use a greedy approach. Maybe we can use a greedy approach. I think we can will be able to solve this question as well. I'll try to do it. I'll take you to my iPad screen first. Illuminate a road. These are the lights. So we are having a lights. First we'll write conditions. For condition V, if bulb is present, then you can check for max of 0 comma I minus V. 2, min of n minus 1 comma I plus V. So it is inclusive. So for J, that is need to take max of 0 comma J, J minus 1 to min of n minus 1 comma J plus 1. Here also it is inclusive. Written the minimum number of additional bulbs required to make every position on the road visible. The first array, the lights they have given as 0 comma 0 comma 0 comma 0. And I plus V, which is the output is 2. So what we'll do is zero comma 0 comma 0 comma 0. We have 0 comma 1 comma 2 comma 3. We'll take one variable last eliminate. Install an additional bulb at position 1. Equal to, and we'll have count of bulbs first thing you will have bulb here. You will have 0 comma 2 comma 3, and we'll be placing the bulb here. last week. So we'll try to paste one here. If max is 0, then max equal to 0 comma j is 0. 2. N equal to is 4 minus 1 comma j plus 1. J plus 1 is 1. 0 to 1. So last eliminated place will be 1. Last eliminated place is 1. We can have first eliminate. And you can take a hash map for the first time and run the first loop to check if there is any light is done for it or not. So for now there is no light anymore. So for 1 we'll make it false. For 2 you are having false. 3 you are having false. It checks. First it checks whether 0 is illuminated. So it is not. Make it